Welcome to lecture number 34 for ECE 461 Control Systems, Digital Control of a DC Servo Motor. Now, what we've looked at in previous lectures was analog control of a DC servo motor. Here we're going to switch over to have it microprocessor or digital control. The motor we're going to be using is the same DC servo motor that we used a couple lectures ago, Clifton DC servo motor, which had a transfer function from voltage to speed of 39 over s plus 6, or from speed to angle, 39 over s plus 6. Here we're going to sample it at 20 milliseconds. When you sample at 20 milliseconds, the analog controller becomes a discrete time controller. Either the first transfer function, when the output is speed, or the second one when the output is angle. Now, again, the hardware will be very similar to what we used before. Before, I had a microprocessor measure the speed compared to my set point, output that to an analog output, then used an op-amp circuit to implement a lead PI compensator that would then drive an AMD 30A8T, basically a big hog and op-amp that drives the motor. Well, anything I can do in hardware, I can do in software, meaning that rather than building an op-amp circuit to implement my lead PI compensators, I'm going to do that in software. The advantage being is if I just change the code, I can add a PI compensator. I can switch over to angle and control the position using proportional or lead compensator. Just a software change does all that. In addition, by avoiding the op-amp, I simplify the hardware, and I don't have the DC offsets that op-amps typically have. The drawback, however, is that I really should be analyzing this in the Z-plane then, since my microprocessor is discrete time, hence Z-plane. So to start out, let's do speed control with gain compensation. If I'm looking at the speed of the servo motor, this is the transfer function in the Z-plane. It's your 39 over s plus 6 converted to the Z-plane with a 20 millisecond sampling rate. With proportional feedback, you just have a gain k. Now note that this is a type 0 system, and hence will have steady state error per step input. If I look at the root locus is actually kind of simple. I've got a pole at 0.88 in the Z-plane. As I increase k, that pole shifts left, meaning that for k equals 0.38, I have a pole at 0.6. As k increases, the pole shifts from 0.4 to 0.2. Let's try that in hardware. Here we see proportional feedback for speed control. I've got a digital controller right now. When I hit the button, I change the set point from plus 50 to minus 50 radians per second. And this is the desired speed of the left column, actual speed right column. You can see that this is a type 0 system, and hence there's steady state error for step input. Responses for placing the pole at 0.6 on the blue line, 0.4 the purple line, and 0.2 on the red line. You see that as the root locus predicts, I get a faster and faster system. This wiggle in there is just the flywheel that I added to the motor. Wasn't perfectly balanced. And this is actually every 2 pi radians per second, one rotation, those little dips that you're seeing. In code, the code is actually fairly simple to implement. I just calculate the error that corresponds to the block diagram, calculate the difference between the set point and the actual speed, multiply by gain, and there you have it. So yeah, this gain right here is whatever you calculate. That determines where the pole belongs. Now that was the type 0 system. Likewise, has constant error per step input. Suppose I use integral control. When I make an integrator, I'll now have no error per step input. And I can adjust the integration gain with k. That changes where you are on the root locus plot. Now to see where you are, I would sketch the root locus of your 0.7404 over z minus 1, z minus 0.8 when I add the integrator. In code, what I would do is cross multiply, and I get z minus 1, bring the 1 right. That's this u right here. U equals u, that's your z minus 1. The next value of u is the previous value of u, plus k times the error, and k is my integration gain. On the root locus, what the root locus predicts is if the gain is really, really small, I'll have a very slow real pole at 0.99. As I crank up the gain, I can speed up the system until I get the breakaway point. Then I start getting overshoot. So we'll check that as I increase the gain k for an integrator. And to show you what that looks like, Here I implemented this in hardware, so this actually has the integrator built in. This is with a pole at 0.99. As I change the set point, when I hit this button here, I change the set point from 0 to 50. I'll be integrating up, changing the speed. This is an example of integral feedback. I'm currently making the set point 0, and it stopped. I now make the set point 50 radians per second, and the integrator slowly ramps up, increasing the speed. And at steady state, it's whatever voltage it takes to force the actual speed to match the desired speed. And you can see that on here. The first column is the desired speed. The second column is the actual speed. And here, I modified the code so I can change the set point from 50 to 40. When the set point is 50, the left column, the actual speed goes to 50. When I change the set point to 40, the motor slows down. You can see that in the right column. And eventually goes to 40 radians per second. For type 1 systems, there's no steady state error for step input. And these are the step responses I get for having it go from 0 to 10 radians per second. Actually, it was from 40 to 50 radians per second, scaled down by 40. By placing the pole at 0.99, when I get a very slow system with a real pole at 0.95 in the z-plane, get a faster pole, no overshoot. And then when I get a complex pole, I start getting overshoot, just like the root locus predicts. Third case is PI compensation. Instead of just using an integrator that adds a pole at +1 in the z-plane, if I add a pole, I can also add a 0. Rather than put the 0 at the origin like an integrator, I can cancel the slowest dominant pole, which in this case is the only pole I have at 0.88. The net result is my closed loop system is just 0.74 over z minus 1. That gives me a pole at +1 in the z-plane, and it shifts left as k increases. It's kind of a fairly simple root locus plot, but again, by adjusting k, I can change the response. In software, the only thing I had to do is, rather than saying that u equals u plus k times the error, that u equals u again is the z minus 1. Cross multiply, bring the 1 right. The next value of u is the previous value of u, plus k times, and now that I have 0, instead of k times the error, it's k times the error minus 0.88 times the previous error. And that places the 0. Here's an example of digital PI control. I've canceled the pole at -6 in the S-plane and placed it at 0.6 in the Z-plane. And notice it is extremely responsive. It's either going 50 or 0 radians per second. You can see that on display. The first column is the set point. The second column is the actual speed. Gets there really, really fast. Also notice with a digital controller, you don't have a DC offset. I tell it to go 50, it really goes 50. You can hear a delta function. That little ping on the motor, that's your delta function getting it to spin and stop. So you can actually hear a delta. If I plot the step response with the PI compensator, again the poles are always on the real axis, so likewise I have no overshoot. If I put the pole at 0.99, I get a slow system like I expect. 0.9, faster system, no overshoot. 0.6, even faster, no overshoot. And the steady state error is always 0. This is a type 1 system. So what this is kind of saying is that root locus really, really works. I'm getting the response exactly like the root locus predict. That's for speed control. Well, I can also do position control. If instead of measuring the speed of the motor, that's measured by pulses per second, if I just count pulses, that gives me angle. If I take the difference between the set point and the actual angle, I'm not controlling the position of the robot, or the motor. In this case, the transfer function that the microprocessor sees would be the transfer function of the motor with a sampling rate of 20 milliseconds, gives you this. Now I can use proportional or lead compensators. I don't want to use a PI because I already have a pole at s equals 0 or z equals 1 in the z-plane. So there's no point adding a second integrator. That just makes things worse. So let's start with proportional feedback. With proportional feedback, I have a pole at +1. That's my integrator. The integral of speed is angle. The pole at 0.88, that's the pole of the motor. As I crank up the feedback gain, the root locus predicts that these poles come together, split apart, and I get complex poles. So as I crank up the gain, I'll get a faster and faster system. In theory, there will never be any error for step input. That's in theory. In practice, it's a little bit different. Because motors are nonlinear, I've got more friction at low speeds. In fact, when it's stopped, I have static friction.
Here we have digital position control. I've got a proportional feedback, trying to control it between 0 and 5 radians per second. When I put it at the breakaway point, there's just not enough gain to get it to move. In theory, this is a type 1 system, should be no error for step input. In practice, the static friction is too large. Crank up the gain to put you at 45 degrees, damping ratio 0.7, and I still have too much static friction. It's not going between 0 and 5 radians. 5 radians is almost 1 rotation. Now crank up the gain to give you 20% overshoot. And I finally have enough voltage, enough gain to get the motor to spin. And there you can see the overshoot. Occasionally it spins and comes back. That's an example of overshoot for a position controller for a motor.
If you measure the actual angle, the red line, compared to the set point, and this is a type 1 system, there should be no error. In actuality, there is an error. The reason being is static friction. If I apply a small voltage to a motor, it won't spin. I need a certain amount of voltage just to overcome static friction. And here the error is small enough that I'm not generating enough voltage to get the motor to spin, and I have steady-state error. So let's try a lead compensator. If I have a lead compensator, what I can do is I can cancel the pole at 0.8 and put it somewhere else. For example, I'll move it down to 0.3. So my lead compensator becomes z minus 0.8 over z minus 0.3, giving me this root locus. If I want to design for 20% overshoot, I'll find out where that hits the damping line of 20%, and that'll be right here, 0.445 plus j.31. Pick k to make the gain 1 at that point, and I get k of 26. So there's my digital lead compensator. What that looks like in software is as following. I'll have to remember the previous output, but instead of being u equals u, that'd be for an integrator, u is 0.3 times u. That's that z minus 3 in the denominator. The next value of u is 0.3 times the previous value. Plus k, that's your 26.8, times z minus 0.88. That's the current error minus 0.88 times the previous error. So that would be the code. And to see what that looks like in hardware.
Here I have position control with a lead compensator, a digital lead compensator. I've placed the pole at 0.6 in the z-plane, and now I'm actually getting decent tracking. It's going between 0 and 5 radians. Here's an example of the lead compensator with position control going between 0 and 1 radian. And in this case, I've got the damping ratio set to 0.7, so you get a little bit of overshoot, and that's what you're seeing.
Note that in that last video, this is what the step response looks like. I get a very quick system, a little bit of steady state error. Again, I've got static friction. That's really hard to get rid of with a motor. But the lead compensator is definitely speeding up the system like I expect. It also reduces the steady state error. It's way better than what we had before, which was here. So all in all, what this is telling you that root locus really does work. It does predict how the system is going to behave as I adjust the gains. It predicts how I can improve the system by adding a PI compensator for speed control or a lead compensator for position control. An advantage of using a digital controller is just using software. I can change the controller. In all those videos, I never changed the hardware at all. I just downloaded a new program, and voila, I had a P, PI, lead, position, speed control, and whatever you want, just change the software. It also removed the DC offset. When I told it to go 50 radians per second, it really went 50 radians per second. And again, the controller is very easy to change. Just download a new program. So that's lecture number 34 for control systems. It's demonstrating that what we're learning really does work in practice.